Hi, everyone. We're waiting for a few more minutes, as Saik already indicated, for the webinar to start. So waiting for a few more people to arrive, probably ending other online team Zoom meetings or other meetings. So we're going to wait for 1, maybe 2 minutes, and then we'll start. Okay, I think we got most in. Hello, everyone. Welcome to this webinar hosted by UReason. I'm Jules Hoekmans, presenting to you today. I have a background in AI starting in the 90s, and I've been involved many times in the past 25 years in prognostic and predictive programs that ensure asset integrity for critical assets and critical processes. On this slide, my contact details. If you have questions after the webinar, don't hesitate to email me, contact me. And please note that the slides will also be shared at the end of the webinar to all the people that registered and attended. So here's my contact details. So I work at UReason, a software company that provides solutions for real-time, condition-based and predictive maintenance, and help our customers daily to use our technology stack. At UReason, we combine our domain expertise and knowledge, software knowledge with our customers, and help them from data from data historians, SCADA, DCS systems, safety systems, CMMS systems, to solutions that enable them to do data-driven maintenance. We have offices in Rotterdam, which we see here in the picture, in the top right, and in Reading in the UK. And our customers are predominantly in the manufacturing and the process industry, and the majority of them are located in Western Europe and the North Americas. So UReason is active in the real-time condition, predictive and prescriptive maintenance domain. Our field of operation is from helping customers to insights into data to helping asset owners, OEMs, and MROs with data-driven maintenance solutions. Our software, APM Studio, is used at different levels in the automation pyramid. So we see here on the screen the automation pyramid, where our software runs, for example, embedded with OEMs monitoring faults and risk in isolation to the asset. And an asset can be instrumentation, an actuator, a pump, a compressor, a filter, etc. But we also work at level 2 and level 3 in the pyramid, where APM Studio is used to monitor faults in relationship to the process. Now, when APM Studio is deployed at level 4, it's predominantly used for optimizing the maintenance costs and the maintenance planning associated to an asset base that supports a process. Today in this webinar, we will have a look at what value you can get from data stored in your process historian for real-time condition-based and predictive maintenance applications. We will first address the question why we need to use the data from the process historian. Then we will detail what data we need. Following this, we will look at how to turn this data into value. And of course, there is also time for questions and answers, but be aware, I will also ask you some questions during this webinar in the form of polls that you can answer interactively. So the first question to ask is, why do we want to use data from the process historian? In a nutshell, maintenance operations wants to know where they are on the PF curve for specific assets or specific parts of assets, and how much time there is before a breakdown or disruption occurs or non-conformity, such that they can have time for a possible intervention. Now, the data stored in process historians can help you finding anomalies that may indicate improper usage, energy losses, but the data stored can also assist you to see how operations actually influences the integrity of your assets. Using process data allows you, and I need to click here in the slide. Using process data allows you to provide early detection of fouling of an asset's degradation so you can prevent these upsets. But the data may not always be used because there are silos of data access in your organization. So let me ask you a first question through the interactions. Do you currently use data stored in process historians for asset performance management type of activity? So you should see a question popping up in your screen, the question, and then 5 answers. So you may frequently use the data in your data historians, or you may not use it, or anywhere in between. So the answers are coming in. Already got quite some answers. A lot of people are answering that they do use the process historian data when there is an upset or an incident investigation. Some of you are also answering that you're currently not using the data. And some of you are also answering that you very frequently use the data that is stored in the process historians for optimizing asset and process performance. It's a bit of a 50-50, I would say, between people that frequently use the data and people that don't infrequently use the data or don't use the data at all. Thanks for your inputs. So the data in the data historians, if you also have failure data or non-conformity data associated with you, allows you to detect potential failures, the P's on the PF curve. And if there's sufficient data and there's sufficient non-conformity data, which can come from different sources, then you should also be in a position to use that data to create models that can inform you ahead of time, early ahead of time, of a potential failure that is upcoming or risk for a potential failure, such that you can take the appropriate actions and prevent the actual failure from happening. So to successfully set up a condition-based, real-time condition-based or predictive maintenance program, you need to access 3 categories of data. You could say that these categories of data are ingredients for a condition-based or predictive maintenance program. You need process data, historical data from your processes collected by a SCADA or DCS or other control system. You need data from your enterprise asset management system or maintenance management system, historical records of work orders, inspection orders from maintenance activities from systems like Ultimo, Maximo, and the like. And what is also an important ingredient is that you need failure data. Now, the failure data is not always available, but very often historical process data from your process historians contains already a number of non-conformities that you can work out, that you can feature engineer based on the data. And I would like to point out that in addition to using process data, analogs and digitals, we also consider alarms and events that are stored, which are violations of thresholds on pressure level, etc., are also quite important. So when we talk about historical data, we talk about data being alarms and events. So there are many traditional process historian vendors, such as OCSoftPy, Esmentech with their IP21 product, the Wonder Historian, ExaQuantum, Honeywell PhD, etc. I mean, there's quite a wide variety of those. And most traditional process historians nowadays use databases, open databases, mostly of them SQL Server based as a backbone. So it's quite easy to get your historical data from these sources. And again, when I say data, what I mean is process data being analogs, digitals, and alarms and events. It's easy, of course, if to get to the data, provided you have access rights within the organization or that someone can collect data from these databases, from these process historians, the traditional ones. There are, however, a few things to keep an eye on when working with traditional data historian vendors. Very often, you see that compression is applied in these traditional databases, which aggregates the data, and certain aggregation functions are applied to the data, which may actually provide you with a somewhat different view on what actually happened. So keep in mind when using traditional process historians to understand how the data is actually stored. Is it stored only when it changes by a certain percentage, or if it's is it stored and is it aggregated over time, or maybe there's even a hybrid approach where it's stored, aggregated over time, and only written to the historian when a certain change limit, a certain change percent has been reached. There's also some new kids on the block to store time series, to store history from your processes. These new kits on the block, such as InfluxDB, Cassandra, PipelineDB, Prometheus, are data historians that typically store all the data, i.e. they don't apply any aggregation or any bending on storing the data. And they provide a lot of aggregations functions on top of the raw data that is stored. Now, let me ask you a question again about what the current data historian or process historian is that you use at your site. So I will start one of these queries again, and answers are already coming in. The first one was AspenTech IP21. InfluxDB, that's interesting to see. It's one of the new kits on the block. Some of you don't know what the process historian is actually at use. This is not uncommon to us. So when we talk to people in operations, they very often know what the process historian is. On the maintenance side, which is somewhat the divide between the OT and the IT environment, maintenance engineers don't frequently get access to process historians, and they actually contain quite a lot of valuable data. So it's one of the things, one of the ingredients that you need for your real-time condition-based or predictive maintenance program. So let me have a look. Quite a lot of you are using InfluxDB, which I find very nice. InfluxDB is an open source time series database, quite efficient, powerful, doesn't change the data that is being stored, but provides a lot of aggregation functions. A lot of you are also using OCSoft Pi. It's one of the common ones that we see around, and yeah, some of you are using others. So maybe following the webinar, if you can let us know what you're using, it would be great. Okay. So typically when you access data from a process historian, you have a reason. Sometimes you may want to do undirected searches to explore data sets to find patterns of interest that you can use in turn to optimize processes performance, asset reliability. You probably do this when you're a frequent user of the data set. Now, when you have a goal to prevent or identify the P's on the PF curve, you typically do a directed search. It's the most common usage. You're looking for something specific in the data set, which may be a process upset that happened, or energy consumption that increased, or excessive wear and tear that you may want to investigate, which was detected, for example, during inspection. Now, when you're doing directed searches and when you're collecting the data from the process historians and collecting data from the CMMS systems, etc., we typically apply a process which is the CRISP-DM process. The CRISP-DM process is a very structured process that was actually set up in the late 90s. And it focuses on understanding, first of all, what the business purpose is of accessing the data. So the business purpose could be, for example, to detect early on wear and tear on bearings in one of your rotating machines, or it could be investigating why there is an energy increase or additional energy consumption, or why there is certain process variations and spikes happening. So the business understanding identifies what the reason is and leads on to data understanding, classifying, what the data is that you're using with. Now, if you're accessing data from your process historians, your CMMS systems, you do it for a purpose to identify a non-conformity or try to identify if you could predict a failure early on, you typically need to add additional data to the data set that you extracted. Additional data that represent the current state, or a label that identifies the type of dysfunction, non-conformity, or failure that you're looking for. So these labels are actually being added for the purpose such that you can, in a different analysis tools, and it's really there's many around nowadays, like KNIME, H2O AI, Python, R, SPSS, SAS, etc. In these analysis tools, you can train and validate models, that provide you, for example, with soft sensor inputs, things that you cannot measure in the process, or things that you would like to very closely monitor if you're looking, for example, for instrumentation failure. But these tools also allow you to train so-called classification models, models that can classify what is currently happening in the process. So you need these labels in order to train and validate a model. And when you've trained and validate such a model, what you really would like to do is also go towards the final steps of the CRISP-DM process, is to actually deploy and start monitoring. And that's what APM Studio provides to you. So APM Studio is an environment in which you can run on streaming data, on real-time data, or on data that is collected from process historians on set cycles. You can run classification, regression models in combination with your best knowledge. Now, let's have a look at an example. So I have data and functional degradation data for various process equipment in my plant. And the functional degradation data is data that was additionally labeled based on CMMS inspection results to the data. And the data from the process historians and the maintenance management systems is combined. And yeah, here we see an overview, a graph of different variables, pressure sensors, temperature sensors, some flow sensors, cooler efficiency, cooler performance. The data itself, looking at the process data, I do not see a clear relationship between the various pressures, temperatures, flows that are measured in relationship to the actual non-conformities that I would like to prevent from happening or detect happening. However, when I look at the relationships of the cooler failures I experience, I do see a clear relationship between a number of variables. So, for example, between the cooler condition and the temperature inputs, between the cooler conditions and the pressures that are being sensed, there's positive correlations and negative correlations. So positive correlation means that when the cooler efficiency or cooler conditions increases, there is also an increase of that other variable, temperature or pressure, and a negative one basically means that it moves in the opposite direction. Now, this relationship is something that from the graph on the previous slide I cannot explain, but I do want to detect it early and be notified of. So what I could do is apply different machine learning techniques to classify a model that would recognize the fault and the degradation when there is sufficient data available to tell me what the remaining useful lifetime is of my cooler. So there are different types of machine learning. There's quite a few different types of machine learning, but one that applies best in this scenario, or that applies best in the scenario of predictive maintenance, is one called supervised machine learning. Um, I have the actual non-conformity outcomes, the failures, the degradations of my cooler. So supervised learning allows you to train a model to recognize those outcomes. So you could consider supervised learning as training with a trainer. the trainer are the labels that you've added to the data set, and the algorithms will actually work out the best function or functions that can actually recognize and correctly classify those specific labels. Now, there's also another flavor of machine learning called unsupervised learning, and unsupervised learning is a somewhat a different beast. The purpose of using or applying unsupervised machine learning algorithms is really to find structure in inputs, to understand when there is non-conformities in the total data set. And then you still need to qualify and quantify why those non-conformities are happening. So supervised machine learning is really the most applicable in the maintenance domain, in the predictive maintenance domain. But there is also other techniques, semi-supervised learning, which mixes both, quite powerful if you don't have a thorough understanding, and reinforcement learning, which is a goal-oriented technique with a reward for the algorithm, but that's not very applicable to our domain. So simply put, supervised machine learning is training with a trainer. The algorithm is provided with the outcome to recognize in the data that, and then is validated on data that is not seen yet. And the outcome in this case is the classification that I will need to add to the data that identifies my cooler condition. So supervised learning is teaching the machine what to recognize and then validating if it can actually recognize it. The opposite, which I mentioned, unsupervised machine learning is quite useful, but it's useful for recognizing groups and deviations from what is or was trained to be a normal operation. So unsupervised learning is less directed and more labor intensive. And that's what a lot of the other companies in this domain also provide. They provide you with a toolkit in which you can flag and highlight anomalies, and those anomalies then on the next iteration that new data arrives will be flagged as important or not important, depending on how you've actually identified those anomalies in their tools. So let's have a closer look at the data and see if there's relationships between the process data and my wear and tear of my equipment, my pumps, my valves, my coolers. What I'm going to do is I'm going to share an analysis environment. It's one of the environments that we quite frequently use with customers because it has a very low learning threshold. So what I'm sharing here is a flow. It's like a flow of different blocks that process the data. So I have pressure data, temperature data, flow data, and I have my labels. I also have cooler data. And each of the different data streams, my cooler data is actually measured at an interval of 1 Hertz, 1 value per second. But my other data sets are actually measured at higher and lower intervals. So I need to do some work basically to merge those data sets and to create one data set, which is done here on the left. Once I've done that, I can start exploring. I can look for correlations, and here in the tool, there's multiple different tools that allow you to analyze the data, but also to do different mining operations, to, for example, train a neural network, etc. So it's a very explorative tool in which you can actually train and validate models. So in this workflow here towards the end, I've set up multiple machine learning streets, as they're called. And one of the streets is actually focused on the cooler. And for the cooler, I've actually found that based on the data, based on the split up of the data that I've done, I can achieve a relatively high accuracy. So give me a second while this dialog is loading. I'm just having a look to see if it's popping up on my other screen. It's popping up on the third. There it is. On the third screen, which is not connected right now. That's interesting. Let me do it slightly different. There's multiple ways of getting to the results. Here we're looking at the confusion matrix. The confusion matrix tells me I have 3 classes that I labeled to my cooler. The class 100 means that the cooler is performing, functioning quite well. 20 means that it's going towards a failure, and 3 means that failure is imminent. There's only very little time before it fails. So the class 100 really represents that, if the model, the algorithm finds a cooler that has a condition that is 100, everything is fine. 20 still gives me some lead time to involve either to do an inspection or to generate a work order, get the work done. 3 really means that people need to start running because the cooler is going to break down and I don't have a parallel line on my cooler. And what we see here is the number of times that the data that was provided to the algorithm had 100% and how it actually qualified at 100% in the data set. So we see that it's accurate. There are a number of times when the algorithm actually misses the right classification, and it's accurate in both directions. So it's accurate in the direction of recognizing the cooler condition being perfect and degrading. 20 is the degrading one, and it's also very accurate to recognize as and when cooler condition failure is imminent. So there are multiple ways in the package to see overall statistics. So this is an overall statistic that provides me with the accuracy. And so it tells me that there is quite a high accuracy. There's maybe even a danger of overfitting this model, but quite a high accuracy of 98%, recognizing, classifying that failure in the appropriate way. Okay, so this is an analysis tool, and when I'm happy with the analysis, when I'm happy with the model that is being trained, what I actually would like to do is to deploy it. So one of the blocks here, which is being put in the workflow, is a PMML writer, and this PMML writer allows me to export the trained model to an XML file, and that XML file explains to APM Studio, our software, how that specific algorithm should be run, how it should be tuned, but also how it can be monitored. So the PMML export, it's one of the 3 different ways in which the machine learning world is currently exporting towards deployment environments. But PMML is the oldest one around, and it also has a lot of support by many analysis packages. So I have an analysis result. It's kind of good. It has a high accuracy, but what I would really like to do is to deploy that. And to deploy that in a way that it can be triggered on the basis of streaming data as and when that data arrives. Now, let me ask you another question. Let's see. Let me start up the question. And the question is about if you have started with a condition-based or predictive maintenance program using advanced analysis techniques. So multiple options again to answer. You've started, or you started but you need assistance, or you want to start, or you want to start but you don't know where to start in the best way. Here, by the way, on the screen that I'm sharing is the view that was popping up on my third screen, which is currently not connected. Sorry about that. So that was a more fancy view that shows the accuracy of prediction in the different stages versus the actual data that was provided to it. And the answers are coming in. So few people want to start. Some want to start and don't know where to start best. And there's also quite a few that have already started. So that's very nice to see. And I'll leave the interaction open for a few more seconds. And we'll go to the next part. Okay, so the exported PMML model that we saw in the analysis environment, which is this red block here, the PMML writer, is something that I would like to use on my streaming data. So the PMML model contains a validated model that can be imported and run inside. And let me show you also in a demo, quite interactive, how I can bring that live. So let's hope it's not popping up on the third monitor. It's not, luckily. There we go. Okay, so here's APM Studio. I have cooler data coming in. I have some other data sets as well. So there's some pump data for pump that speed, the suction pressure, voltage, current flow. It's an anonymized data set. So the IO points, normally tags, have been translated into normal text, readable text, so to say. And I have a few data sets. Those data sets are read into APM. They're applied to objects following a certain class model. And let's have a look. Let's have a look first at the output. So here we see a dashboard. The dashboard provides me with, for my critical equipment in this specific setup, the current pump performance, my current cooler health status, some main properties, and some time series chart here that identify where the performance of my curve currently is, the red dot, and how it's been evolving over time. What my net positive suction head is of my pump, how many alarms I have of a high level count, a medium level count, etc. And I can zoom into these different assets. So for example, I can zoom into this pump and I can see that there is data flowing in, changing, pressures. I can also have a look at where this pump is located. So this pump is currently located in our office in the center of Rotterdam. I can have a quick view at the charts, at the different cycles that the pump has gone through. I can have a look at the alarms, drill into that, etc. And these alarms, of course, can also be communicated directly to your CMMS system, to an Ultimo, Maximo, SAP, and others using REST interfaces. So this is more, a view that you could provide, for example, to a field engineer. Now, behind APM Studio, to support this, there's a number of different things running. So, for example, for the pump, there is a bow tie running. So, bow tie is a cost consequence model that will continuously, based on the data that arrives in APM Studio, um, um, validate and look at different causes and how valid those different causes are. So, for example, it's accessing data from vibration sensors to determine if there's bearing failures or impending bearing failures. It's looking at the discharge pressure, suction pressures, etc., to determine if there is a likelihood, in this case, this bow tie, of pump cavitation. And then the right-hand side of the bow tie, the consequences can then help you, if that event actually takes place, also to mitigate and monitor the barriers to prevent additional failures or additional non-conformities from happening. So everything within the APM Studio environment is set up what we call in a low coding type environment. So I'm going to take this into edit mode to quickly show you. And I also got a notification saying that I'm almost at the end of the time, so I need to hurry a little bit. So everything is done in a graphical manner. You can click, drag, and drop. For example, let's say if I would like to run a machine learning model that identifies certain calls, I can just click, drag, and drop this calls block. I can configure it. I can tell it how likely this is to happen, how it should calculate its likelihood. And then in the control block, there's different palettes, different blocks available that allow you to define different tasks, the different checks that need to be performed in real time on the streaming data that can come from MQTT sources, OPC databases, etc. And there's different blocks, different functions. So, for example, this is the PMML block that allows me to identify if there is a likelihood of a pending failure of my cooler. Um, so that's it. It's in a nutshell. In a nutshell, um, what APM Studio allows you. Here we actually see the exported model of my cooler condition that relies on a number of inputs. One of them is efficiency, the cooler power, some volume flows, and as and when data arise, my cooler condition is being determined and is being forwarded, and messages can be generated then either to a CMMS system or can be seen directly here in the interface of APM Studio. So the different failure codes, 100, 20, and 3, 100, of course, doesn't lead to an alarm, but 20 does, and 3 does as well. And we're running historical data in a loop back here, so you see a lot of these events. My cooler is really not in a good condition, you could say, but that's because I'm running at increased speed the data set at the moment, and it's currently concluding that a failure is imminent, and on the basis of this, you could still start a work order. Now let me ask you a final question. Just trying to get my mouse to the other screen. I've got an issue with screens in this session. So final question, and then there is 2 more slides coming. I'm wondering if you want to bring your analysis results, so the results that you obtained using different analysis tools, be it Python, R, SPSS, etc. If you would like to go towards deployment, because the real value, of course, of doing all these initiatives is to take your analysis results, validated models, and bring them live and use them 24/7 instead of only concluding afterwards post-mortem that the item failed. So I'll leave the question open for a little bit longer, and the responses are diverse. People are doing this and already have a solution. People are doing this and looking how to. For some of you, it's not relevant at this time, and some of you don't know at this point in time. So that's there's diversity in the answers, which is also good. It's interesting. The majority is looking how to do this. So it's one of the areas where together with our customers, very often in co-development, we work, we help, and assist our customers in this path, in this journey. Okay, so that was the demo within APM Studio, a software environment that provides you with capabilities to in real time monitor your assets, do condition-based and predictive maintenance programs. If you don't have sufficient non-conformity and failure data, or you cannot label it at this point in time, you can of course start with doing real-time condition monitoring on the basis of your rules, your engineering knowledge about the assets and the processes. And with the demo ending, we have actually come to the end of the webinar. I would like to thank you for participating. There's now time to ask questions, and once I stop the webinar, you will also be presented with an evaluation form, a very short form, on which you can indicate what you thought about this webinar, what other topics you would like to see addressed, how valuable, invaluable it was to you, etc. So I really appreciate it if you could fill that in. That would be great. And I'll have a look now, and I need to turn to Carlos and Arthur for that, I think. No, Carlos, for questions from the audience. So, okay, Saika was the first. Do you want to bring your analysis results online 24/7? So one of the questions. So, yeah, the analysis results. If let's say if you have a classification model that provides you with an indication of a certain non-conformity or a certain pending failure, so the P's on the PF curve, if the accuracy of those models is high enough, then it's quite valuable bringing that online 24/7 and combining that with your engineering knowledge, your deterministic knowledge. And the bow tie models that I showed very briefly are quite a nice means of doing that, because they probabilistic reason over the outputs of the ML models, the outputs of your engineering knowledge, which could be very simple trend monitors, or they could be simple threshold violations, and combining those. And yeah, bringing that online and back to an inspection order or work order for a specific asset is what we do daily. what we do daily for our asset owners. And yeah, it is something. It's one of the things to do 24/7. Of course, if you're in the process industry that runs 24/7. Okay, there's another question here. What is the best way to prepare my data from my process historian for usage in the analysis package you showed? Yeah, so the analysis package, so I showed NIME. Many of these analysis packages have default interfaces, standard interfaces to file-based and database systems. So let's say you have a exaquantum process historian underneath its SQL Server. Same goes for Wonderware historian. Pi really depends on the version, but it could be Oracle, could be SQL Server, it could be the proprietary Pi time series database. But the nice thing about most of the analysis packages is that they provide database interfaces out of the box. So you can interface quite easily to a copy, I should say a copy of the process historian and load data into NIME. If you do not have a direct database connection or a copy of the database, you can also use file-based approaches. And most of these analysis packages also allow you to connect to different big data database formats as well. So that's kind of nice. It's quite easy. Another question is, I'm a young computer science engineer working in hydropower asset management. I feel like data historians are like dinosaurs of data storage, especially compared to new time series database solutions. However, it seems to still be a standard in our field, and I'm missing something, or are there advantages to are there only advantages switching to newer solutions? No, you're not missing something. The industry in the 90s and a little bit prior to that as well, because of regulation purposes and all kinds of other reasons, started storing historical process data, analogs, digitals from the process. And at the time, 25 years ago and a little bit longer ago, storage space was costly, and special databases, proprietary databases, had a play to provide very optimized, from a storage point of view, very optimized solutions that would allow you to store time series data over a longer period of time, over a year, 5 years, 10 years, etc. And yeah, this was adopted by industry, to quite a great extent. And these historians, if it's Pi, IP21, XQuantum, etc., they have a continuous role or different roles in different work processes at the customer side. So it's not that easy to break out or replace a data historian at a site. It's not that easy. Even if from a technology point of view and a cost point, financial point of view, the new kids on the block, the new process historians are very cheap or certain even free. It's very often not the right argument to do a replacement, because those process historians have been paid for, they have been used, they've integrated in many other different work processes. So it's not something that is going to be easily replaced. So switching to new solutions, there are definitely advantages, financial ones, performance, not having aggregation, not having having clear, real, raw data, all advantages. But the positions of the existing process historian vendors, the older ones from the 90s, is quite strong. There's another question here. In general terms, which amount of time can be seen for a transition between states, 120 and 3, e.g. hours, days, and week? Okay, yeah, so this is a question specific to the cooler data that I was showing. So in the cooler data, 100 meant that the cooler was fine, was doing perfectly. When the cooler data had a label of 20, so a failure was going to happen and there was still time to plan. In that case, in that specific customer case, there was 7 to 10 days before the cooler failure would occur in a distributed fashion. 3 meant that there was 12 to I think it was 36 hours before the cooler failure would actually occur and happen. So 3 was a really, an emergency one, one that shouldn't happen but did happen from time to time. When the cooler condition 20 was detected, there was still plenty of time for that specific customer, a few days, few weeks to plan and take actions appropriately. There's another question here, do you or could you speak of figures of cost reductions? Yeah, it's an interesting one. So cost reductions have, there are different types of reducing costs. So sometimes real-time condition monitoring predictive maintenance programs are run to reduce manpower. The goal is not to reduce manpower, but access to skilled, experienced manpower becomes more and more difficult for a lot of operating companies. And so sometimes the programs are run to become more efficient with a same size or smaller size team. So there are cost reductions in FTEs, full-time employment people, range from saving 10% to 50% FTEs, but it really depends on the case, and it really also depends on the depth and the breadth in which the PDM program is being rolled out. Now, that's on the labor side. There is cost reductions, potential cost reductions also on reducing the number of inspection rounds, optimizing the condition-based maintenance tasks, reducing emergency repairs, of course. But one of the larger cost reductions is in actually moving towards more performance-based operations. Performance-based where risk and integrity of the assets is known, and there is less unplanned downtime. And that's in my experience, in our experience, the biggest saving for most companies is preventing unplanned downtime. And we have different cases. I mean, we have cases with in dairy industry where unplanned downtime is not very costly, so to say, but there's a lot of costs that are associated with purging and cleaning when certain unplanned downtime events happen. In oil and gas, in certain cases, unplanned downtime can be expressed in millions of dollars per 24 hours. So reducing unplanned downtime there by 2 to 4%, and we've done certain cases there where we reduced it by 13%, is quite valuable, is quite worthwhile. Let's see, looking at the other questions. Okay, here's a question. I do not have alarm data stored in my process historian. Does this mean I cannot start? No, absolutely not. So when I said historical data earlier on in the slides, process data and alarms and events. But what you will find, especially in the traditional process historians, is that alarm and event data is not always stored because there were other event alarm historians that fulfilled that role. It really depends from system to system, but not having your SCADA or DCS alarms is not blocking. They really help, but you have to keep in mind that if you would draw how a control system, SCADA or DCS or PLC-based control, how that protects the assets, it's protecting the normal operation of the asset. So that's the first circle. If you would draw a circle outside of that, a second circle, that's the circle where the integrity of the asset is actually being affected. And the third circle outside that is the safe operating window. So the normal operating window and sometimes the integrity operating window is what alarms of that you will find in your alarm history. If you don't have that, it's okay. You can start with the CMMS data, focusing on the high cost, high frequency items in combination with data from your process historian. But I would recommend to also see if you can access maybe part history, or maybe even the settings of the SCADA system, DCS system, with respect to alarms, such that you could emulate what alarms would have happened. They are a value, but you can start without that ingredient. So if we're cooking pasta, you can do it without salt, and salt is of a certain value, I would say. And same goes for alarms and events. Okay. Okay. I see that we've answered all the questions, and I'm 1 minute late. We should have stopped at 12:20. I'm gonna stop the webinar now, and I thank you again for your attention. I really appreciate it that you were able to attend. You had questions. If you can provide us with feedback to this webinar, once I stop the webinar, you get an evaluation form. It would be really great. I hope you all have a good day and stay safe. Take care. Bye bye.